Lubicz, cross change of level and applications to isogenies.
Thank you very much, John. Thank you for the organizers of the INTS conference. I would like to apologize for not giving this talk in person, but unfortunately, I had a passport renewal problem. So I come to the subject of my talk, which is about fast change of level algorithm and application to isogenies. And this is a joint work with Damien Robert. So the aim of this talk is twice. I would like to present you what is a change of level algorithm for theta functions, and give you at least one application of this change of level algorithm to obtain general efficient isogeny computation algorithm between Abelian varieties. So I think that most of you must have some acquaintance with the general problem of isogeny computation between Abelian varieties. But the problem of change of level algorithm might be less well known. Nonetheless, this is a problem that we came upon with Damien while working on improving isogeny computation algorithm, and we find it interesting for its own sake, and we think that it has other applications beyond just computation between Abelian varieties. So the results that I'm going to present in this talk apply to a fairly general situation. I'm going to consider Abelian variety of any dimension over any base field. Maybe that I have to exclude the case of characteristic 2. But in this talk, we will specialize to Abelian variety over C for the sake of simplicity. So first, a basic definition. What is an Abelian variety? This is a smooth, complete, connected group variety over a base field K. Concretely, an Abelian variety is a subset of the projective space, which is given by the finite number of homogeneous polynomial, and it comes together with an Abelian group law, which is given by rational functions. Examples of Abelian variety are elliptic curves, which are nothing but Abelian variety of dimension 1. If C is a smooth curve of genus G, Jacobian is an Abelian variety of dimension G. And if the dimension G is greater than 4, it is known that not every Abelian variety is a Jacobian, which means that Abelian variety in a way are generalization of Jacobian varieties. So as I said before in this talk, I consider Abelian variety over C, and it can be shown that in a way they are parameterized by the Siegel upper half space, which is the set of G times G matrices with coefficient in C, which are symmetric and which imaginary part is positive definite. If omega is such a matrix, then we can consider the lattice, the sublattice of CG, which is given by ZG plus omega ZG. Then what I call an analytic Abelian variety is just the quotient of CG by this lattice. And it can be shown that every principally polarized Abelian variety over C is isomorphic as an analytic variety to an analytic Abelian variety. So far, I've just given you the definition of an analytic Abelian variety, but I would like to consider them as algebraic variety. And for this, we want to consider projective embedding of these Abelian varieties, of these Abelian analytic Abelian varieties. And in order to do so, it's easily seen that it's enough to be able to define enough quasi-periodic functions with respect to the lattice which defines the Abelian variety. This motivates the definition of what I call a lambda quasi-periodic function of level n, which is a function of CG, such that for all z in CG and lambda in ZG, the function f verify the two quasi-periodic relations of my slides. It's easily shown that the set of such functions form a vector space over C, which I denote by Rn omega. So this is where a theta function comes into the picture, because we are going to be able, using theta function, to build bases of these level n quasi-periodic functions. So we are going to consider theta function with rational characteristic for a, b element of Q to the G. The theta function with rational characteristic a, b is a function of the domain CG times the Siegel upper space, which is given by the power theory expansion in exponential that you can read in my slides. And from this power theory expansion, one can prove easily some quasi-periodicity relation for theta function with rational characteristic. And as consequence, we can build bases of the level n theta level n quasi-periodic functions with the help of theta function with rational characteristic. So this is in my definition for n greater than 2. We can consider the n to the g level n theta functions, which are denoted by theta e of z, which are defined with the help of theta function with rational characteristic. And it can be shown that these n to the g theta function form a basis of the level n quasi-periodic function with respect to lambda omega. As a consequence, if the level is greater than 3, one obtain a projective embedding of the analytic Abelian variety defined by omega into the projective space of dimension n to the g minus 1, just by evaluating in a point z of CG these theta functions. And the image by this projective embedding of the 0 point of the Abelian variety plays an important role in the theory. It is called the theta null point. We more about this later on. So we have enough definitions to give you a first flavor of what I call a change of level algorithm. Let L and N be positive integers. What I call a change of level algorithm is an algorithm to compute a theta basis of Rn omega of the level n functions, the level n quasi-periodic functions, from the knowledge of the level Ln quasi-periodic functions. This is for going down from level Ln to level n, and the other way around for going up. So there are previous results in that direction, which take the form of formulas. For instance, the well-known and very important for the theory of theta function duplication formula can be seen as a formula to go from level n to level 2n and the other way around. And there is a generalization of duplication formula, which is due to Koizumi, which can be specialized to obtain a formula to go down from level Ln to level n. But okay, and the aim of this talk is that we want to expand these results and to improve the complexity of the change of level algorithm that we obtain from this formula, especially the complexity of the Koizumi formula, because this formula is obtained by considering the Koizumi formula involves a summation on the kernel of a certain isogeny, which is defined on the product of Abelian variety. And this product depends on the congruency of L modulo 4. And this is frustrating because we recover this congruency in the generalistic isogeny computation algorithm, although we don't see where this congruency of L modulo 4 has nothing to do a priori with the computation, the isogeny computation that we want to do. So we would like to get rid of this congruency modulo 4. So far, I've given you a first flavor of the change of level algorithm, but there is still some analytic stuff embedded in the definition, because there is this omega that would like to get rid of. And this is why I'm going to talk about the algebraic representation. How are we going to manipulate our Abelian variety? Actually, that will be given by the theta null point, which is a point on the projective space, and it is rational. And from the knowledge of this point, by using Riemann equation, which are parameterized by this theta null point, by a result of Mumford, one obtain a complete set of quadratic equations from the projective embedding of the Abelian variety inside the projective space. And still using a Riemann equation, one can recover the arithmetic of A inside the projective space. So we have a complete description of the Abelian variety as an algebraic variety, just from the knowledge of the theta null point. It means that we have equation, and from the knowledge of two projective points, we have formulas to compute the addition of this point. And in this regard, with this point of view, the theta functions can be regarded as a section of a certain very ample line bundle that I call L to the n, because it is the nth power of a certain principal line bundle. So it is clear from what I've said before that omega is a more from the knowledge of omega, one can recover the theta null point, but we would like to understand what extra structure we have, what extra knowledge we have on the Abelian variety when we give it by its theta null point. In this direction, we have a theorem of Mumford-Kempf, which tells us that if n is greater than 4 and even, if we look at the locus of the theta null point, which is just the image of phi n omega, when omega is going through all the elements of the Siegel upper R space, then we get an embedding of the moduli space that I've called, what I have denoted by AG of n in my slide, which is the quotient of the Siegel upper R space by a certain congruence subgroup of the symplectic group with coefficient in Z, which is called the Iguza level n subgroup. And so it means that as the data of a theta structure gives you not only the abelian variety, but also polarization for this abelian variety, and also a level n structure on this abelian variety, and some extra information that I do not detail here. So from what I said previously, we obtained that the following data are equivalent. So the data of a theta null point, the data of a point of the modulus space AG of n, and it can be shown that this is equivalent to the knowledge of a suitable basis of a very ample line bundle on A. And we call, after Mumford, this equivalent data a level n symmetric theta structure. So if theta n is the level n symmetric theta structure on A, we denote by phi theta n the associated projective embedding. And in the rest of this talk, you can you have to think that in order to obtain the data of a theta structure is, from an algorithmic point of view, it's just the knowledge of a theta null point of the abelian variety. So we have a technical definition of what we call compatible theta structure that I'm not going to elaborate, because this is you can find the details in the paper. So we can now have a more detailed description of our results. So if L and N be two, let L and N be two relatively prime integer, and we suppose that we are given an abelian variety together with a level Ln theta structure. From the knowledge of its level Ln theta null points, it's easily seen that by using the action on this theta null point of the theta group, that one can recover, and it's effective, one can recover the whole L torsion of the abelian variety. And even more than that, we can recover a symplectic decomposition of this L torsion for the veil pairing. So one can ask if, if we are given a level A together with a level n theta structure by its level n theta null point, and suppose that we are given a symplectic, the L torsion, and a symplectic decomposition of the abelian variety for the L torsion, can we recover the level Ln theta null point? So we answer yes, by yes, this question in our paper, and we give an algorithm which, from the knowledge of the level n theta null point, so, and the data of the L torsion, which is given by its point in the projective space, which is defined, which is given by the points in the projective space, because the level n theta null point gives us a projective embedding of the abelian variety, and we can recover a level Ln theta null point at the expense of order n to the g, L to the 2g, log of L operation in the base field. And we have a similar result for going down from level Ln to level n with complexity in the order of n to the g, L to the g, log of L. So an immediate application of this change of level algorithm concern the general problem of computing isogeny between Abelian varieties. So the problem is the following. So we are given an Abelian variety and K, an isotropic subgroup of the alternation of A for the veil pairing. And we want to compute the quotient of A by K and the isogeny from A to B. So in terms of representation, A will be given by its theta null point of level L, n. So by just n to the g projective coordinates. And K is given as a subvariety of A inside the projective space of the correct dimension. So to compute isogeny, we have at least the following general algorithm. So in dimension, we have the well-known, so for the case, the elliptic curve, we have the well-known Veluz formulas, which are linear in the size of linear complexity in the size of the kernel. And we have a general algorithm in dimension G to compute isogeny, which is due to Cossé, Robert, and myself. But you can see here that the complexity of this algorithm is linear in the size of the kernel only in the case that L is congruent to 1 modulo 4. And you can see that in the case that L is congruent to 3 modulo 4, we do not have anymore an optimal complexity. And this is due to the use of the Koizumi formula in this algorithm. In the same way, in dimension G, we have algorithm to compute cyclic isogeny, which is due to Dudo, Jedzef, Robert, Vuil, which is also linear complexity in the size of the kernel. But this algorithm is not very practical because there is a step in the algorithm where one has to recover a product theta structure and product of Abelian variety. And for that, one has to try all the symplectic matrices over Z over NZ, where N is the level of the computation, which is painful to say the least. So even if it has nothing to do with the size of the kernel, it makes this algorithm. It makes that this algorithm has a big constant in the complexity. And in dimension 2, we have an algorithm of Couvain to compute L isogeny, which is linear in the size of the kernel, but it is specialized for Abelian varieties of dimension 2. So what is the link between this isogeny computation algorithm and the change of level problem that I've give you a flavor of? So in order to compute isogeny, we start from A together with a projective coordinate system, which is given by a level n data structure. And in order to express the isogeny, we have to undo B with also with a level n data structure to have a coordinate system in order to express the isogeny. So there are two approaches in order to do so. First approach is to compute the pullback of the theta structure on A by the contragradient isogeny of F, which gives a level Ln theta structure on B. And then go down from level Ln to level n with the first red arrow of my diagram, of the first diagram of my slide. A second approach is to go up from level n to level Ln on A, and then compute f with the isogeny theorem for theta functions. So in my diagrams, the black arrows correspond to the use of the isogeny theorem for theta functions, which is perfectly effective and well understood. But unfortunately, this isogeny theorem does not preserve the level of the theta structure. This is why we have to compose it with a change of level algorithm. And this is what we have improved in our paper. As an immediate result, we obtain a general isogeny computation algorithm, which is always linear without any condition on the kernel with the size of the kernel. And we avoid this cumbersome computation in the computation of cyclic isogeny, which makes the algorithm much more practical. So in terms of representation, in practice, as I told you, the Abelian variety will be given by their level, by their theta null point. So we, in practice, we want to work with the smallest possible level because we want to have the more compact representation of the object, and we have to deal with even level because we need to use Riemann equation to represent our Abelian variety and compute arithmetics on it. So in practice, there are two levels which are interesting. Level 4, which gives you, which deals with 4 to the g coordinates and gives a projective embedding of the Abelian variety. And in level 2, we have a more compact representation with 2 to the g coordinates, but we do not have any more projective embedding of the Abelian variety, but rather of its associated Kummer variety. And the computation of level 2 or 4 theta null points can be done by using Thomé-like formulas if the Abelian variety is given as a Jacobian of a curve, or by picking up a point of the model space of Abelian variety together with a level 4 theta structure. A projective description, effective description of it is given with Riemann and symmetry equation by a result of Mumford. So there are two implementations available: a magma implementation, which is called Avail isogeny by Bisson, Cosset, and Robert, and the Sageman implementation by Anna Somoza. All the detail and link to implementation are in the paper. And I will finish this talk by give you some other hints about other application and open question. So other application of change of level algorithm, from this change of level algorithm, we can use Thomé formula to obtain higher level theta functions. And they also can be used to compute modular function of arbitrary level. And there are two open questions. So we have excluded the case L equal to 2 in our algorithm. I think it would be interesting to treat this case. And okay, there is something that coisomy and duplication formulas that there is something that these formula are doing that our algorithm is not doing well. They are computing actual value of theta function where our algorithm actually computes the projective theta null point, which means that these algorithm can be used to compute modular forms, and this is important in some applications like in the IgM algorithm, whether this algorithm or generalization of the IgM algorithm, whether this algorithm is on finite field to compute the number of points of a curve defined over a finite field, or if this algorithm is used to recover the period matrix of a Jacobian of a curve. So thank you for your attention.